Another plethysmography is based on electric impedance measuring. It is simple to attach electrodes to segment of tissue and measure the resulting impedance of the tissue. Instead of using such a blader and something that like that a chamber, air control, volume measuring, we can use impedance measuring because the volume of the tissue affects the impedance of the tissue. As the volume of the tissue changes in response to pulsation of blood, or the resistivity changes in response to increased air in the tissue, for example, in the lungs, the impedance of the tissue changes. Electric impedance plethysmography has been used to measure a wide variety of variables, but in many cases the accuracy of method is poor or unknown. Let's talk about the principle of electric impedance plethysmography. First of all, let's look at the structure of the electric impedance plethysmography method. We put the limb inside our electrode arrangements. Here we have 4 electrodes. 2, 4 apply a constant current, and 2, 1, 4 record the applied voltage, and we can measure the impedance by dividing voltage over current. This is a simple way, but we should consider some assumption. The derivation requires 3 assumptions. The expansion of the arteries is uniform in healthy vessels, not in diseased ones. The resistivity of blood, ρ B, does not change. We assume that resistivity of blood does not change. In fact, ρ B decreases with velocity because of alignment of the cells with flow streamlines and movement of cells toward the axis. Also, ρ B is real for DC, but a small reactive component at high frequency will be generated. Also, we assume that lines of current are parallel to the arteries. This assumption is probably valid for most limb segments, but not for all knee. In the system, we know the accuracy often poor or unknown. Okay, let's talk about some formulation and electric equations. You can see we have the limb segment here with an initial cross-sectional area. The electrodes located here, the length of the limb segment is L, and we measure the impedance with a Z meter. We have an initial volume, an initial area, cross-sectional area, an initial volume, and additional area because of the blood injection inside the limb segment, and also the volume variation you can see, and we want to formulate these events. Okay, the shunting impedance of the blood ZB is due to the additional blood volume, delta it should be delta V that cause the increase in cross-sectional area delta A. The impedance for this shunting impedance can be written as this, and the delta V, the additional blood volume here, is L multiplied by delta A and can be calculated by this equation. We must replace the ZB of figure 8.17b in terms of the normally measured delta Z, because we measure a Z at initial state, and after the pumping, after the additional blood volume injection inside this limb segment, we have an additional impedance, and we want to measure this one, not this parallel one. Therefore, if you write the equations, you can find that delta Z is something like this. And as you can see, the value of the delta Z is negative. You know, when we parallelize an impedance to another, the total impedance will be decreased. Therefore, the delta Z in this structure should be negative, and the delta V can be calculated based on this equation, because this assumption, this is a true assumption also, and the delta V can be calculated something like this. Remember that delta Z is negative, therefore we need another minus sign here to have a positive additional blood volume here. And now you can measure the changing in volume based on changing in the impedance. It is desirable to use a current greater than 1 milliampere in order to achieve adequate SNR. At low frequencies, this current causes an unpleasant shock. However, the current required for perception increases with frequency. Therefore, frequencies about 20 kilohertz are used to avoid perception of current. That's not harmable, but we should avoid perception of current. The skin electrode impedance decreases by a factor of about 100 as the frequency is decreased from low values up to 100 kilohertz. High frequencies are therefore used to decrease both the skin electrode impedance and the undesirable changes in this impedance that result from motion of the patient. If a frequency much higher than 100 kilohertz is used, the low impedance of the stray capacitance make design of the instrument difficult. And a normal setting for this electric impedance plethysmography is this. The current between 0.5 to 4 milliampere in RMS, and frequency is between 50 to 100 kilohertz. In electric impedance plethysmography, we have two choices for the number of the electrodes. we can use 2 or 4 electrodes. For reasons of economy and ease in application, some impedance plethysmographs use 2 electrodes, as shown in figure 8.18, and as you can see, the current I flows through the same electrode same electrodes used to measure the voltage V. As you can see, the voltmeter is connected to the same electrodes. But this causes several problems. Weighted impedance of the tissue near electrodes, pulsation of blood in the tissue cause artifactual change in the skin electrode impedance, and the current density is not uniform in the region of interest. So the normal method for measuring the voltage instead voltage over current cannot be used because we don't have any uniform region of density, region of current density. To solve these problems, clinicians use the 4-electrode impedance plethysmography shown in this figure. As you can see, the current flows the 2 outer here. The current flows these outer electrodes so the current density is more uniform in the region, as you can see here, sensed by the 2 inner voltage here. And variation in skin electrode impedance cause only a second-order error. We use a constant current source and a voltage sensing amplifier and other circuits. Applications of electric impedance plethysmography have been listed in this slide. Electrical impedance plethysmography is used to measure a wide variety of changes in the volume of tissue. Electrodes placed on both legs provide an indication of pulsation of volume are normal. A clinically useful non-invasive method for detecting venous thrombosis in the leg is venous occlusion plethysmography. Electrodes on each side of the thorax provide an excellent indication of rate of ventilation, but they give a less accurate indication of volume of ventilation. Such thoracic electrical impedance monitoring is widely used for infant apnea monitoring to prevent sudden infant death syndrome, SIDS. Electrodes around the neck and around the waist cause a current to flow through the major vessels connected to the heart, impedance cardiography. An 8-electrode catheter in the left ventricle injects current through band electrodes 1 and 8 and measure voltage from all electrodes in between. Some systems claim to measure body water and body fat by measuring the electric impedance between the limbs. As you can see, electric impedance measuring is an important with various application method. In electric impedance plethysmography, we can utilize multiple electrodes. The number of independent measurements for n electrodes is equal to n multiply in -1 divided by 2. For example, if we place 16 electrodes around the thorax, we can obtain 120 independent measurements and can use these data to compute a two-dimensional image of resistivity distribution within the thorax. The spatial resolution is only about 10%, but this electric impedance tomography may be useful for monitoring the development of pneumonia, measuring stomach empty, or monitoring ventilation. The advantage of electric impedance plethysmography are that it is non-invasive. That's so important, and that it is relatively simple to use. The disadvantage are that it is not sufficiently accurate. For many of the attempted application, and that even the cause for change in impedance is not clear in some cases. The accuracy, the problem of accuracy is so important. In many cases, electric impedance plethysmography or other types of plethysmography is only used for finding the rate of the changing, not the exact and accurate value of the volume. But we can monitor the changing in the volume. The last type of the plethysmography we will consider in this lecture is photoplethysmography. Light can be transmitted through a capillary bed. As arterial pulsation fills the capillary bed, the change in volume of the vessels modify the absorption, reflection, and scattering of the light. Therefore, we can use this structure, this theory, to fabricate a plethysmography-based device. We called it photoplethysmography. As you can see, we have two types of photoplethysmography. We have bones inside our finger, and we can put a lamp here, an LED, for example, an IR LED, and because of the reflection of the light, because of the bone here, we can receive the reflected of the light, and the pulsation, the arterial pulsation, which fills the end of our distal part of the finger, the capillary bed. This pulsation will change the volume of the fingertip, and now we can use our device to monitor the variation of the volume at this point because of their absorption, more absorption while pumping, while pulsation. And now you have a device to monitor the pulsation at the distal part of the limb, the finger. The second structure, we have a transmitted light here, a light lamp LED here, and the photosensor at this place, and because of the pulsation of the arterial vessels and the changing in volume, we can find the changing of the volume inside the ear because of the changing in reflecting, scattering, and absorption of the light inside our ear. Although photoplethysmography is simple and indicates the timing of events such as heart rate, it provides a poor measurement of change in volume, and it's very sensitive to motion artifact. This is a good method for finding the rate, but not the accurate volume. We cannot calibrate this measuring because it provides a poor measure of change in volume. We cannot calibrate it. Pay attention, we cannot calibrate it. In this slide, you can see a simple circuit we can use for platysmograph. In this photoplethysmograph, the output of a light-emitting diode here is altered by tissue absorption to modulate the phototransistor. Here we have a tissue here, and the light passes through a tissue, and the volume of blood inside the tissue will affect the travel light. Therefore, we can find the changing of the volume inside the, for example, finger by detecting the received light at the photo the transistor. And also the DC level here is blocked by the capacitor. This is DC, not DE. And switch S restores the trace. A gallium arsenic LED is used as the light source with narrow bandwidth of 940 nanometers. In the photoresistor, photosensor and infrared filter is used to prevent visible light interfaces. We usually use IR LED here. And also high-pass filter is used to eliminate large baseline values. You can see the example 8.6. Photoplethysmography can be used for a patient who remains quiet. The plethysmograph can measure heart rate. That's good. Remember that we cannot measure the volume. We can only find the heart rate. It offers an advantage in that it responds to the pumping action of the heart and not to the ECG. In some cases, we have proper heart function and the ECG is generated, but we don't have any pulses at the distal part of the limbs, for example, at the fingertips. In these cases, we can use photoplethysmography to find this problem. Also, when probably shielded, it's unaffected by the use of electrosurgery, which usually disables the ECG while an operation. When we use electrosurgery, we cannot use ECG because we have plenty of interfaces. Therefore, we can use something like a photoplethysmography, which is based on photo and light, and this method is unaffected by the use of electrosurgery. Okay, but when the patient is in a state of shock, vasoconstriction causes peripheral flow to be greatly reduced, and the resulting small output may make the device unusable. To prevent this problem, the device has been used to transmit light through the nasal septum. This technique monitors terminal branch of the internal carotid artery, one of the most important artery inside our body, and yields an output that correlates with the cerebral blood flow. Okay, this was the last page of our last lecture, and thank you for your attention.